Okay, so we're going to be looking at Riemann sums. And when we talk about Riemann sums, we're talking about left sums, right sums, and midpoint sums. So to find the area under the curve of some function, what we're going to do is we're going to basically draw some rectangles and we're going to add up the areas. So rectangle areas are really simple. It's just length times width. And so what we're talking about here when we talk about this sum, all right, and I'll highlight that there for you, it just means add all of this stuff up. All right, this next component, f of x sub I, just means, well, for that particular rectangle, what was the height? And the delta x is what actually stays the same between all of the rectangles. And that is the width of each of the rectangles. So how do you find that out? Well, the delta x is found by taking the final value in the interval that you're looking at minus the initial value of the interval and dividing by the number of rectangles that you're asked to construct. So what we look at here in this problem, or in these examples here, and if you look at them all, they're all sums with 10 rectangles that are being drawn. Okay, we're looking at left, right, and midpoint, or left, midpoint, and right, I should say. So the first value is 0, the last value is 5. So you're taking 5 minus 0, which is 5, and dividing it by 10. So 5/10, which is 1/2. So each delta x, if you will, and let me just zoom in for you so I can write it in. Each delta x is going to be half a unit. Okay, and that's going to be the same for all of these graphs here. All right, so we just zoomed in there. So that's how you would calculate the area under the curve. It's really simple. If you know how to calculate the area of a rectangle, you can do this advanced calculus stuff. All right, so don't sweat it. You can do it. All right, but let's talk real quick about left sums and then right sums, and then we'll take a look at some examples. So what I want to point out is that a left sum will produce an area that is less than the true area when a function is increasing. So if you notice, the function here is increasing. A left sum produces rectangles below the curve, so you are actually underestimating the area. Now, if the function happens to be decreasing, all right, and you're doing a left sum, notice you are now overestimating the area. All right, so notice it says there excessive area. Now, the opposite is true for the right sum. If the function is increasing, a right sum will, again, overestimate in this case. And if you are looking at a decreasing function, the right sum will be an underestimate of the true area. Okay, so just some things to note about when a function is increasing, decreasing, and which sum you're using in particular. So we're going to take a look at 3 examples, one of each of these varieties, and we've got some graphs to help illustrate what it is that we're looking at. And then hopefully it makes some sense here to you. So again, the function that we're going to be utilizing for all of these is x squared. And if you looked at a previous video that I made about upper, lower, and mid, it's quite similar. All right, but these are a little bit more common, I think. The more common notion is for you to use left, right, and mid Riemann sums. Okay, pretty much the same thing, except it's very specific as to what you're looking at. It stays the same. Upper and lower, well, you have to analyze the function to determine, well, which one is the maximal value or the minimal value. Riemann sums left and right is pretty clear cut. All right, so look at here. It says f of x equals x squared between x equals 0 and x equals 4 using a left sum. So I'm going to highlight that, left sum, with 2 rectangles of equal width. So the first thing I'm going to do is I'm going to calculate my delta x value. My final value is 4, my initial value being 0. And I'm going to divide that into 2 rectangles. So that means my delta x is 4 divided by 2, which is 2. So I'm going to cut this in half right here. And if I'm using a left sum, that means that I am going to use the leftmost value of the function, that right here being 0. So notice it's actually going to have a height of 0. All right, so that right there, the area of that rectangle is 0. Now we create another rectangle. This one, we'll start then at the leftmost value, which is 2, because from 2 to 4 the leftmost value is 2. So then the height of that rectangle there is going to be this value here, which is 4 units. And again, the width here is going to be 2 units. So when you calculate the area under the curve there, well, that's pretty simple. That's pretty straightforward. You're just finding 4 times 2. And that's the area of under this curve here. All right, so let's figure this out. The f of x sub I value, in this case, being 4, and your delta x being 2. All right, so 4 times 2 happens to be 8 units squared. All right, 8 units squared. So I'm going to box that in. And just for the sake of the notation here, I'm going to write in that this is f of 4. All right, I'm sorry, not f of 4, f of 2 times delta x. And we could also add in the fact that we did find f of 0 and multiplied that by delta x here. And I don't need to write that, delta x. But what ends up happening, this was 0 times 2, which is just 0. So we don't even consider it. Okay, so no need really to write it. Okay, so the answer there being 8 units squared. All right, let's take a look at another example very similar. All right, in this example, we're looking at f of x equal x squared between x equals 0 and x equal 1 using a right sum. All right, with 2 rectangles of equal width. So we're looking from 0 to 1. All right, let's see here. What do we get? From 0 to 1, that means we're going to have a delta x with a final minus initial of 1 minus 0 divided by 2. So that's going to be half. I will write that as a decimal, 0.5. There we go. All right, we have that right there. And now what we're going to do is we're going to draw our rectangle with a right sum touching the rightmost corner. So from 0 to 0.5, the rightmost corner is 0.5. All right, there we go. And try to clean that up a little bit, make it a little more straight. And then from 0.5 to 1, the rightmost value is the one at 1. Okay, and then we draw another rectangle there. So now we've got 2 rectangles. Notice we are definitely overestimating because the function is increasing. All right, so we're going to calculate that area there. And let me kind of finish shading it in so you can see what we're doing here. There we go. All right, now let's calculate. All right, how do you figure this out? Well, you plug in your value at 0.5, so 0.5 squared, that's going to give you this value right here, 0.25. That's the height there. All right, but the width is going to be 0.5, our delta x, and that's going to be the same width here. All right, this one, when we plug in 1, we get 1 squared, which is 1. So there is our 1. So when we calculate our values here that we're going to add up, multiply and add up, we're going to have f of 0.5 times delta x plus f of 1 times delta x. And f of 0.5 is a quarter, 0.25, and delta x, of course, being 0.5. We calculated that again at the beginning. Plus f of 1, which is 1. Okay, 1, and delta x again being 0.5. Okay, so we get this right here, and we just multiply those two, we add it up, and we get something like this, 0.625 units squared. Okay, so that right there serves to be our area under the curve from 0 to 1 using 2 rectangles of equal width and using a right sum. So let's take a look at one more example here. All right, so we've got this example here, number 3. We're looking at f of x equal x squared between 0 and 1 again, this time using a midpoint sum with 2 rectangles of equal width. So what we're going to do, we're going to first calculate our delta x here. Our delta x being final minus initial, 1 minus 0 divided by 2. Again, we have half, a decimal, all right? 0.5. All right. But in this case, we're going to look at half and we're going to mark off the midpoint of that. In this case, it's going to be a quarter and 0.75. So that's where we're going to draw the height of our rectangle at. So right about there. Okay, it's not perfect, but I did try. And then right about there. Okay, again, it's not perfect, but I tried. All right, so we're going to calculate these areas. All right, so maybe it's under, it's over, but it kind of compensates when you're over and when you're under. All right, we're going to calculate those areas right there. Let's figure this out. So a quarter squared, because we got to plug it into x squared, this is going to give me something like 0.0625. Okay, and of course that's the height. The width of this is going to be half a unit, and then this is also going to be a half a unit, but the height here is going to be 0.75 squared, which is about 0.5625 right there. Okay, so now what we do is we are going to plug all of that into our summation formula here. We're going to say f of 0.25, we're going to multiply it by delta x plus f of 0.75, and again multiplied by delta x, and we plug in the numbers that we just calculated. 0.0625 times 0.5 plus 0.5625 times 0.5. All right, you do that on your calculator, you're going to get something like this: 0.3125 units squared. So again, these are some really nice examples on left, right, and midpoint sums. Let me highlight this one, that it was a midpoint. Okay, left, right, and midpoint sums, Riemann sums really, and they're really not that bad, and you can apply this to various examples. You know, analyze the graph, look at the function values of the calculator. It's really not difficult at all. So as always, I hope this video was helpful, and if it was, remember, like and subscribe.